Next speaker is Abolfazl. Simorgh. So go ahead.
Okay. Hello to all. I'm Abolfazl Simorgh, a PhD student under the supervision of Professor Manuel Soler, and today I'm going to present our latest progress on the topic of robust aircraft trajectory optimization and climate change. So I'm going to start with a brief motivation. Aviation is contributing to climate change through the emission of CO2 and other non-CO2 emissions, and this contribution is estimated to be at 3 to 5%. And of this contribution, 1/3 is associated with CO2 emissions, and the remaining 2/3 is associated to non-CO2. But if you look at the confidence interval, it's highly uncertain. Accounting for a strong growth rate of aviation industry, which has already been recovered from COVID pandemic, a critical increase in its associated climate impacts is expected. Here we see an example of formation of contrails as a largest contributor to the non-CO2 climate effects. Contrails are line-shaped clouds from water vapor that condense and freeze into ice crystals. During nighttime, they trap thermal radiation from Earth, so it has warming impact, but during day, it can also reflect incoming solar radiation, so it can contribute to cooling. And as for mitigation strategies, currently we have several solutions planned or being introduced to mitigate the corresponding impact. The technological, policy-based, and alternative fuels are efficient solutions are required for environmental sustainability of aviation industry, but they face challenge from implementation point of view. So they generally considered as medium to long-term solutions. But we know that 2/3 of aviation-induced climate effect is associated with non-CO2 emissions, and these non-CO2 effects has a strong dependency on the atmospheric condition at time and location of emissions. So it's possible to identify areas which we expect that aircraft emissions have large climate impact and incorporate this information to plan or to reroute these sensitive areas to mitigate the climate impact. So operational measures, more specifically flight planning, is a way to go. And it is feasible within the current infrastructures and also be considered as relatively immediate solutions. So this is the scope of my PhD, which is on trajectory planning considering climate effects. So in the first phase of PhD, we did a state-of-the-art study and we identified several gaps. So here I'm going to mention three that is the focus of this thesis. The first one is the consideration of uncertainty. So recent studies were all deterministic, so they have ignored the uncertainty effects, but these climate-sensitive areas are highly uncertain from climate science, from meteorological data, and from emission calculation. And then there is a need for robust planning. So include these identified sources of uncertainty into the flight planning and be able to incorporate this information and efficiently in terms of computational time provide solution. And the last one is lack of non-CO2 climate effects indicator. We need to see to what extent climate optimal flight planning is efficient and what are the implications. So we aim to address all these three in this thesis. So first, why uncertainty is important. As mentioned, non-CO2 climate effects are highly uncertain. And when we are deviating from cost-optimal trajectories or business-as-usual trajectory, we are increasing the operational cost, fuel consumption. This means that we are increasing CO2 emissions, which we know it with more confidence. And also, it has some side effects on the manageability of air traffic operations because we may reroute all the flights to reroute a specific area, so the workload or complexity will increase. So we need to be more confident when we are deviating from cost-optimal trajectory. Here we can see some scenarios. I'm going to just present one. So imagine this red trajectory is the cost-optimal, and this area is the predicted climate-sensitive areas. So we reroute trajectory, the green one, but in reality, no climate hotspot is observed. So we are increasing cost and CO2 emissions, but the non-CO2 climate effect won't be changed. So we need to generally avoid false decisions. This means that we need to account uncertainty effects and plan trajectories in a robust manner. So robust climate optimal flight planning. Here is the contribution. As mentioned, in the first phase of the PhD, we did a state-of-the-art study. We formulate a flight planning problem, including climate impact, uncertainty effects. In the second phase, we develop an optimizer for structured aerospace. It's a GPU-based optimizer, so it's really fast, and incorporates meteorological uncertainty to deliver robust climate optimal trajectory. For the third year of the PhD, we develop another optimization based on optimal control. This is for free routing aerospace. And in the fourth year, we want to develop incentivizing indicators for the non-CO2 climate effects through some large-scale analysis. We perform different large-scale analyses, but the focus of today is only on one, the first one, large-scale analysis based on ACCF, which I'm going to present in the next slide. Here is the optimization scenario. So we are performing trajectory optimization for all days in 2022, two different departure time, midnight and midday flights because of different behavior of countries' climate impact. And we consider top 150 routes. For the climate impact, we use algorithmic climate change functions, a model to get familiar with, to understand about climate sensitivity to aircraft emissions. Basically, ACCF takes as input meteorological data and provides some sensitivity maps like this for different species, which we will incorporate into flight planning tools. And here is the overview of what we are going to present in the next slide. So this is the results of the optimization. We start with Pareto frontier. It has uncertainty areas, but I don't know why it doesn't appear in the presentation. So here, the horizontal axis shows ATR20, which is the climate impact, a metric for climate impact. And vertical axis shows the increase in the operating cost. We have departure at midnight and midday, and it is clear that a strong daily variability can be seen in the mitigation potential. For example, in specific months like October, we can have up to 35% reduction in the climate impact, but for example, in July, it's about 10%. Also, we can see the differences in the departure time. Such variability is mainly due to the variability in the meteorological conditions, because non-CO2 climate are highly dependent. And on average, we can see the 80% mitigation can be achieved by accepting 0.5 increase in the operating cost. And the least mitigation potential is associated with summer, these red guys. And in this, to explore the result more in detail, we picked two different points along the Pareto frontier. One of them is the climate optimal trajectory associated with 0.2% increase in the operating cost. The other one is the green ones, climate optimal trajectory associated with 10 times higher increase in the operating cost, which means 2%. In the next slide, we want to explore this more in detail. So here we can see the monthly changes in the climate impact mitigation potential. We have two different routing options here. One of them is the cost optimal, and the other one is the climate optimal, allowing for 2% increase in the operating cost. The rows shows the climate impact of different species, daytime countries, nighttime countries, water vapor, NOx emissions, and net climate impact. We can see that the mitigation is generally achieved through contrails. How? We can see that for daytime flights, the contrails is red here, the impact of daytime, which means the contrails during the day is warming, originally based on cost optimal trajectory. But for the climate optimal one, they are turning to blue, which means that we are creating cooling contrails. For the night, since the formation of warming contrails is not possible, formation of cooling contrails is not possible, we are avoiding forming contrails. We can see that the red ones are turning to white, which means that we are avoiding contrails. And if we check the other non-CO2 species, for example, for NOx emission, we don't see that much changes. So the message is that climate optimal flight planning is mostly effective at mitigating the climate impact of contrails. So for NOx emission or other non-CO2 species, maybe it's better to go for other measures such as technological or alternative fuels. And here is the last slide about results. Here we're focusing on the climate impact mitigation on daily basis. Again, we can see a large variability on different days. And in the second figure shows the percentage of the flights required rerouting from cost optimal or business as usual trajectory. A correlation exists. For example, here we see that for this specific day, we can have 60% reduction in the climate impact, but look at the rerouting, 50%. So when we have high mitigation, we need to reroute more. This means that we need to smartly allocate extra cost and reroute in order to gain mitigation while being operationally feasible. For example, during summer, there is no mitigation and the number of rerouting is lower, and this is important.
You need to
get
finished.
So, yeah, we have another analysis, large scale analysis, such as what happens to the flight profiles or correlation between the background meteorological condition and the mitigation potential. If there is any question, I have them in the backup slide, and we can answer them in the question answer session. So regarding the outcomes, I've already published 4 papers. One is under review and 2 is in the preparation phase. And for the conferences, we attended several conferences, and also I was a developer or co-developer of 3 open source Python libraries on the results I show. And I've been participating in 3 European projects, and I did my stay at Delft last year. And about the next step, finalize 2 in preparation papers and finalize the thesis and defend. Thank you very much for your attention.